Hello, I'm Professor Steve Miller. Today I want to talk about the Reynolds stress model, which came out in 1995, of Hanjalic, Jakirlic, and Hadzic. This is a particular high Reynolds number approach, which is based on solving differential equations for, of course, the Reynolds stress, or transport equation for Reynolds stress, which is shown right here in equation 16, which I introduced and derived earlier in this video series. We need to go in and model the particular terms on the right-hand side. And if you don't recall these particular terms and all their forms, I'll try and write down the equations again here and there, and go back and look at that video series. So we have to look at each of these particular terms. Of course, in this form, we're trying to track particular variables, which is ui prime, uj prime bar, correlation. And we'd have to have 6 equations because it's symmetric. So let's examine this modeling in terms. First of all, for the triple correlations, these authors have modeled them as 2 correlations, second order correlations. So the third order correlations are modeled as second order by Cs k over epsilon, that's turbulent kinetic energy divided by dissipation, mu k ul prime bar, and partial ui uj bar, partial xl. So this uses the idea of a generalized gradient diffusion hypothesis to make this model for the triple correlation. Here, CS is set to 0.22 through calibration. And really, this model is based on the known or modeled second order correlations, because of course we're trying to solve for these particular correlations which appear in our RSM transport equation. Let's look at the pressure diffusion term, which is the first term on the right-hand side of 16, Dij, and then we'll look at the other terms afterwards. So pressure diffusion, we might model it and write it out as partial xk of the quantity viscosity plus Cs coefficient, k over epsilon, uk prime, ul prime bar, partial ui prime, uj prime bar, partial xl. So this model is for pressure diffusion, and you'll note it only contains second order correlations. And so really there's no particular modeling even happening in 87 on the first term on the right-hand side of equation 16. Let's look at the second equation. You'll see that this has second order correlations with pressure and velocity components, which must be modeled. And it's proposed to expand out phi ij into 4 terms. The first one, phi ij1, 2, and then phi ij1 and 2 at the wall. That's what the superscript wall means. That's not a power. So let's look at the first one. The first one's modeled after the famous Rota's return to isotropy hypothesis. That meaning if we have anisotropic turbulence and if we're not disturbing it, then it'll slowly decay and return to isotropy. The way this is modeled would be with this form here in 89, phi ij of 1 equals negative C1 constant times dissipation times Aij. And we discussed the form of Aij in a previous lecture video, but to remind you, it is the anisotropic tensor, which is often modeled as negative of the eddy viscosity mu t divided by turbulent kinetic energy times the Kronecker delta function. So Rada in words, this return to model hypothesis might be worded as the anisotropic turbulence will tend to return to isotropic turbulence via the redistribution of energy via the pressure strain force. At least this is like the basic words and description of this equation 89 for the first term of the breakout of phi ij. Let's look at the second term, phi ij2. This is what we call the rapid distortion portion, and it's modeled by the isotropization of production hypothesis. Here is the particular model that the Hja turbulence model RSM uses. It's phi ij of 2 is negative C2, Pij minus 2/3 pk Kronecker delta function delta ij. Here pk is written as 1/2 pii, so this is repeated indices, so that's really 1/2 of the trace of Pij. So this actually model form should look familiar to previous models and sort of like the stress tensors of the equations of motion. So near the wall, we have to define the last two terms here of 88, I believe. I didn't number it, but C and D here. So you get the same two terms near the wall. And we can model using HJ model, Phi-J1 and Phi-J2, and they propose these very complicated forms with C1 constant, C2 wall constant, some functional forms, which we'll define in a minute. And we'll just look at one. They're both rather complicated, and you'll have to refer to the paper for the full description of how these change the flow near the wall, but we'll describe that, just a basic idea, in a second. We have UK prime, UM prime. We have these normal vectors. So N is the normal vector from the wall. So here's a wall, and the boundary layer, of course, flows in this direction, perhaps. There's a normal vector N bar. So N, I, N, J, N, K, or LMN, are these components of the normal vector near the wall. Delta ij minus 3/2 ui prime uk prime bar, and k and j minus 3/2 uk prime uj prime bar, and k and I. There's a similar form for 92. So this is sort of like penalization, if you will, of Phi-J1 and Phi-J2 for the returning anisotropy for 1 and the rapid distortion for 2. So let's look at these functions. Fw for the wall is a minimum of k to the 3/2 over 2.5 epsilon xn, and xn is the distance to the wall. So you see, before this calculation even can start, it's very much like some other models where you need to know the distance to the wall, which doesn't work too well in very complicated devices. So I would argue, just based on this point, this is a non-closed model, right? Because it depends on something not to do with the flow of physics. It has something to do with the distance to the wall. And of course, fluid particles don't really know how far they are from the wall. So, other constants in the model we just looked at, C1, C2, C1 suit W, C2 suit W. These are nothing but constants. And what happens in follow-on models, other authors who followed on this model propose functional forms for these coefficients. Here, for the HJJ model, they define some of their functions, coefficients, as something that depends on the turbulent Reynolds number. So I'll just list their constants here. We have C1 equals C squared to AE, C2 equals 0.80 squared to A, C1W equals the max of 1 minus 0.7 C, or 0.3, and CW is the minimum of A and 0.3. What's A and E? I'll show that in a second. These constants depend on further constants. C equals 2.5 A F to the 1/4 little script f. Big script f is min of 0.6 or A2, and f equals min of RET 3/2 or 150 or 1. So these seem to be coming out of thin air, but they're, of course, chosen somewhat empirically to make adjustments to better match data sets of experiments. Here, E, capital E, is the dissipation anisotropy tensor, and it goes as 1 minus 9th of E2 minus E3. E2 are these tensors Eij, Eji, and Eij is now defined as epsilon ij over epsilon minus 2/3 delta ij. Wow, so this is really just kind of a different form of the dissipation tensor. And so we should note that just like we're tracking Reynolds stress components, 6 of them, we're also tracking essentially 6 corresponding dissipation rates for those 6 Reynolds stresses in the Reynolds stress tensor. And you see they're normalized by epsilon. Nonetheless, large A is 1 minus 9/8 A2 minus A3. A2 creates a similar form. Remember, A is the anisotropy tensor, and A3 is Aij, Ajk, and Aki. So it's a similar form between E and A, but A is just tracking the anisotropy tensor, and E is tracking the dissipation. Okay, now let's look at how that dissipation tensor is modeled, because it seems to have introduced some new variables, so they have to close that part of the system. They'll say epsilon ij is Fs, epsilon ij sup star, times 1 minus Fs, 2/3 of delta ij epsilon. So you see here's Fs and 1 minus Fs, and they're being added, so you know this is sort of like a fractional form. Here, epsilon ij star is this huge term, and I'm not going to read it out to you, but that's also something I recommend referring to the paper, which I referenced in the video comment or description. Here, Fs is 1 minus square root of a, e squared, and Fd is 1 over 1.1 RET. Now, you'll note that for isotropic turbulence, we'll find that Fs will go to 1, and Fd will go to 0. And therefore, these terms, if we put them back in and rewind the video if you want to see epsilon ij again, it'll reduce to 2/3 the Kronecker delta function of epsilon. And so you can imagine we're basically recovering the trace of the dissipation tensor, which is good. And that's part of the reason this model is formulated this way, to recover isotropy. So what does this mean in the terms of the formulation? This means that the dissipation tensor will follow 6 particular components, and indeed is related to the scalar dissipation, which is what we derived originally, the dissipation equation. Now we need a specific dissipation equation for this closed form so we can track scalar dissipation, and that's what equation 99 is. It's a transport equation for dissipation, and on the left-hand side you see a velocity, u sub k, and we have partial epsilon, partial xk on the left-hand side. And all these terms on the right-hand side we've essentially already modeled and looked at before, except for some new coefficients. Their epsilon tilde is epsilon minus 2 nu viscosity, partial square root of k, partial xj, partial square root of k, partial xj. So these calibrated coefficients are C epsilon 0.18, C epsilon 1, 1.44, C epsilon 2, 1.92, C epsilon 3, 0.25, with F mu equal to F epsilon 1 equal to F, our unity, and F epsilon 2 is this function here, where RET is the turbulent Reynolds number. You'll see there's particular terms which are added to equation 99, which aren't exactly physical. They're added to make corrections relative to data and capture better measurements. One is S sub L, and that actually is named after Yap. It's the Yap Correction Factor, which is well known, and that was produced in a paper in 1987. And basically what happens, it slows the growth of the scales in near regions of separation, that the growth of turbulent kinetic energy be too large, so it limits it. And the other value, which we'll see in a second, is the so-called correction by Hanjalic and Launder in 1980, which is another paper. So here's the form of the Yap correction factor, which is inserted on the right-hand side of the dissipation equation to limit growth. And this S epsilon 4, this Hanjalic and Launder model, there's different forms for this, but this one's formulated for boundary layer flows, generally in the streamwise direction. And it's definitely important for aeronautical applications where there might be relaminarization or increased turbulence in the boundary layer. So this will help better predict relaminarization. That's the overview of the three-dimensional. Let's get back to the top. That's the overview of the three-dimensional HJH model in 3 dimensions. And I encourage looking at the paper and those 2 other papers by the authors, and of course Yap, to understand the extra terms. And a few other comments is this model is obviously a lot more equations than a simple 1 or 2 equation model, and it's a lot harder to program and validate, and hopefully it would give better predictive results, especially for more complicated situations. Thank you very much for your time today. I'm Professor Steve Miller.